Number 45. Find the mass of Jupiter based on data for the orbit of one of its moons and compare your results with its actual mass. All right. So in question 44, I derived this formula that I'm going to use in this problem. I won't go through the derivation again just because I just did it. I'm going to be literally repeating myself from question number 44. So if you want to know how to arrive at this, please feel free to check out that question. It's number 44 here from chapter 6. But I'm going to begin the problem here with that formula, okay? So the mass of Jupiter in this case will be equal to the radius between Jupiter and one of its satellites cubed multiplied by the angular velocity of one of its satellites around Jupiter squared, all divided by the gravitational constant. So let's go to the table and pick out any satellite, aka moon, you like. I'm going to choose Europa. All right, so this is going to be my row there. So the mass of Jupiter then will be equal to the radius between Jupiter and Europa. And here's the average orbital radius, right? In this column, it's 6.71 times 10 to the 5 kilometers. But, so I need it in meters, right? So I'm just going to add 3 to the exponent there. That's equivalent to multiplying it by 1,000. So 6.71 times 10 to the 8, all right? That's going to be it cubed. Then multiplied by now the angular velocity. Well, they don't give us the angular velocity, but they do give us the period. And what does the period represent? Well, the period represents the time it takes to go around or make one revolution, right? So Europa revolves around Jupiter one time in 3.55 days. So I can say that one revolution here per, well, let me do it this way. Omega would then be one revolution, right, per 3.55 days. All right, 3.55 days. Now remember, this is basically an angle measure per time, right? It's a degree change per time. So that is the definition of angular velocity. I mean, even look at this, right? Theta per time. So let's get rid of revolutions. They go on the bottom, radians on the top, 2 pi radians for every one revolution. Bing, bang, boom. Bing, bing, bang, bing. I'm getting a little loopy here. It's getting late. So they're gone. Now we got to get rid of days. So days goes on the top, hours on the bottom, 24 hours in a day. And then I'm really trailing off here, hours to seconds, 3,600 seconds in an hour. Okay, and let's do that math. This is going to be 2 pi divided by 3.55 times 24 times 3,600. And we get a value of 2.05 times 10 raised to the negative 5. And that's in radians per second. All right, that is the value of omega. So this is the value I'm going to plug in. So let's plug that in. So we have now 2.05 times 10 to the minus 5. And square that, and then divide this whole thing by the gravitational constant, 6.673 times 10 to the minus 11. And let's see what we get. The mass of Jupiter. And we get 6.71 times 10 to the 8 cubed times 2.05 times 10 to the minus 5 squared, all divided by 6.673 times 10 to the minus 11. And look at that. We get a value of 1.90, right? 1.90 times 10 raised to the 27th power, and that's in terms of kilograms. Excellent. And notice I wrote down over here what the mass of Jupiter is, right? I think I rounded there a little bit. It's like 1.898 maybe times 10 to the 27th, but look at how close it is. Now, the interesting thing that is that it doesn't matter. If you chose any one of the other moons here, you would have gotten basically the same answer. Very similar though, right? I mean, these numbers are rounded, but you would have been right in that ballpark. All right? So guys, thanks so much for tuning in. Please remember to subscribe. Look forward to helping you out with the next question. Take it easy.